This video is going to explain the difference between a mathematician and an engineer. In education today, the push is for a combination of science, technology, engineering, and math, STEM, integrated into the curriculum. It is an important concept. It's important to be able to do that, but it's also important to understand the significant differences between those disciplines. And to look at those differences, I've put together an example of one problem, and we will see how the engineer solves the problem, which is right here. And then we will see how the mathematician solves the problem, which is right here. You will see that there is a significant difference in the way that they approach the problem, the way they deal with the complexity of the problem, and how they solve it. Also, you'll see that there's a little bit of a different use of technology between the two, and how they take advantage of technology, how they use technology, and how they think. Well, let's get to it and see the details of how it works. Okay, I am an engineer, and I am looking at an engineering problem. I have two poles. This pole is 15 feet tall. This pole is 25 feet tall, and they are 30 feet apart. And I have been asked to calculate the minimum length of cable. If there's a cable that goes from the top of this pole to the ground and then back up to the top of this pole, I need to calculate the minimum length of that cable. So I'm looking at the minimum of L1 plus L2, and I'm just going to call that capital L. So I need to find the minimum length of that, and then also I want to find out X value, how far I am from the 15-foot pole, or 30 minus X, how far am I from the 25-foot pole. Now, as an engineer, I'm excited because I get to do a minimization problem. It's exciting. I'm going to develop equations, take derivatives, set them equal to 0, find local minimums, and in general, just have a wonderful time. So as I start to approach this, I realize I've got two right triangles. So I can find L1 and L2 using Pythagorean's theorem. So L1 is going to be the square root of 15 squared plus x squared. And L2 is going to be the square root of 25 squared plus 30 minus x squared. So my goal is going to be to minimize L1 plus L2. So let's just write that as capital L, and I'll do some simplification. So 15 squared is 225 plus x squared plus, and I'm going to write out these terms. So 25 squared is 625. And then 30 minus x foiled, 30 squared is 900 minus 60x plus x squared. Now, as an engineer, I could take the derivative of these, set the derivative equal to 0, find where that 0 is, that x value, plug that x value back in, and find L1 and L2, but since I'm an engineer, I'm going to take advantage of technology. So what I'm going to do is I'm going to graph this length function, and then I will find the minimum of that graph because I'm an engineer and I'm going to use technology. So let's start by plugging in the equation. So it's going to be the square root of 225 plus x squared. That's awesome. Plus the square root of 625 plus 900 is 1525 minus 60x plus x squared. Okay, I've got my equation. I'm going to graph it. Of course, my calculator set up to the standard window 1010. And I don't want to think too hard about this, so I realized that x has to be somewhere between 0 and 30. So actually, let's go into the window and make x from 0 to 30. And I really don't know what y is going to be. It has to be positive, so we'll go 0. And I'll just go 100 just because I don't know and I don't want to waste a lot of energy trying to think about it. So we'll just look at a standard graph here. And we can see that we've got a little bit of a dip here. But yeah, because my scale is off, it's kind of hard to read. So I'm going to change my y 40 to 60. So if I change my y 40 to 60, x is 0 to 30, I should get a pretty good representation of the graph. Now, so this graph is the length of L1 plus L2. If I take the derivative of this, it'll be the slope. So the slope is going to be 0 right here at the minimum. Well, my calculator, as awesome as this is, allows me to calculate the minimum. So I just have to do a left bound and a right bound. So we'll come over here. Keep going, we'll do a left bound. And we're pretty far left. Oh, come on, stop. Pretty far left. And now let's go over and look at a right bound. Sorry for all the clicking here. Okay, so we've got a right bound, and you know what, because this calculator is awesome, I really don't even have to get that close on the guess. So I'm going to guess. I'm just kind of taking shortcuts here. There's my guess. So we calculated the minimum as at 11.25 and y is 50. So let's go back over here. L is going to equal 50. X is 11.25. So we have 11.25 here. And then over here, 30 minus 11.25 would be 18.75. But the minimum length of our cable is going to be 50 feet. Okay, this is the way an engineer would approach this. I recognized it as an optimization problem where I needed to minimize a length. To minimize a length, you need to come up with an equation, find the local minimums or maximums, in this case minimum, because we're trying to find minimum length, and do a quick, could have done the derivative. I'm an engineer. I took the shortcuts of the tools available to me, and that is the way that I approach the problem. Okay, now I'm going to make a copy of this, and let's look at how, oh come on, how Mathematician would look at it. So let's erase all of this. So let's go back to the text. This was 15. Let me erase that. This was 25. And then this bottom one is 30, but I'm going to write it right here, 30 feet. Okay, so the engineer looked at it as an optimization problem. Let me just kind of explain to you how a mathematician would look at this. A mathematician would look at it and they wouldn't immediately jump to, I have to do an optimization. They would say, are there other ways to look at this problem? And let's say, just for argument's sake, that this is the surface of water or something reflective. And then let's take this 25-foot pole and bring it down this way, and this 15-foot pole and bring it down this way. I'm going to take away these lines for a second. And so this is 25, 30, 15. Let's look at if we took a red line and went from there to there, red line, and went from here to here. Now, had I actually drawn these to scale, this would be right there, so our reflection would be right there. Okay, so had I drawn it to scale, this is what it would look like. So what we see is if you take your poles and your wires and you reflect them across the ground, whatever you want to call it, the distance between reflected down here and the top of this pole has to be a straight line. So this x point right here, whatever x is, and whatever 30 minus x is over here, that would give you the straight line. But let's even go one step simpler. If I were to just redraw a right triangle right here, you could very easily say this is 40, this is 30, so the hypotenuse will be the square root 40 squared plus 30 squared, which is 50. Or, interestingly enough, this is a 3, 4, 5 triangle. So the mathematician would look at conceptually how maybe he could redraw a diagram, and what we ended up with was if you redraw it so that you have a rectangle, a triangle, looks like this, it gives you the same answer. It's just a different way to look at the problem, much easier way. So if you look at the total amount of calculations that I did right here as compared to the calculations the engineer did, and oh, by the way, I used the calculator to shorten that. So that would be two different approaches for how to look at the same problem. Now that you've seen the difference between a mathematician and an engineer, I hope you can appreciate that even though you need to integrate how you do, what you do, why you do it, there are still significant differences between the mathematician and the engineer. They both use math. They use math differently, but they use the same math. I hope you've enjoyed this little demonstration, the difference between mathematicians and engineers. Have a wonderful day. God bless.